A heavy test dummy drops through open air toward a surface that looks perfectly harmless. Below it, the water is flat, blue, and glassy. There are no rocks, no sharp edges, no visible wall, just water. Then the dummy hits. The surface dents for a fraction of a second, as if the entire pool has become a stretched sheet. A white ring blasts outward. Spray rises in a violent crown. Under the surface, a column of bubbles punches downward like a collapsing tunnel. The dummy does not sink gently into the water. It slams into it, forces it aside, and loses speed almost all at once. From far away, the scene looks impossible. Water is supposed to give way. Water is supposed to splash. Water is supposed to be soft. But at high enough speed, the problem is not that water has become solid. The problem is that the falling body has arrived too fast for the water to move out of the way gently. The surface does not need to become concrete to be deadly. It only needs to stop the body too quickly. The first clue is in the splash. A slow hand entering a pool makes a small ripple because the water has time to flow around the fingers. A fast object gives the water almost no time. The liquid has mass, and that mass resists being accelerated before the object can enter. It must push a path through millions of tiny moving particles. The faster the impact, the more violently that path has to open. At low speed, water flows aside. At high speed, water fights back with inertia. The dummy drops again in slow motion. This time the camera is closer. The feet of the dummy touch the surface first. The water caves inward under the first point of contact. A thin sheet of spray peels away. Then the rest of the body follows and the surface erupts. Nothing here is magic. The water is still water. It is not turning into a solid wall. It is simply being asked to move out of the way in a time so short that the force becomes enormous. That word, force, is the real center of the scene. A falling object carries motion. The faster it moves, the more motion and energy it has to lose at impact. When it hits water, that energy does not disappear. It is transferred into spray, waves, bubbles, sound, heat, deformation of the body, and violent acceleration of the water itself. The dangerous part is not only the speed, it is the stopping. A body falling through the air has gained speed over the entire fall. Then, at the water's surface, it may lose much of that speed over a very short distance and a very short time. The shorter the stopping distance, the harsher the deceleration. The harsher the deceleration, the greater the forces that pass through the body. A car crash works the same way. A seatbelt, airbag, crumple zone, or foam barrier does not make motion disappear. It stretches the stopping process over more time and distance. Water can sometimes stretch that stop when the entry is controlled, narrow, and specialized. But in a high-speed, uncontrolled impact, the first contact can be brutally short. The water does not politely open. It has to be driven open. The dummy falls flat in a controlled test shot. This time the back hits first. The splash is wider. The shock ring expands faster. Instead of a narrow path cutting downward, a large surface area strikes the water almost at once. The water has to move aside over a broad shape. The force is spread across more of the dummy, but that does not make it safe. A wide impact can deliver violent force through the chest, abdomen, pelvis, spine, and internal organs. The skin may not be cut. The injury can happen inside. That is one of the most frightening parts of high-speed water impact. Water may leave no sharp wound, but the body can still be stopped with crushing suddenness. Internal tissues keep moving when the outside is slowed. Organs, blood vessels, bones, joints, and the spine may experience forces they were not built to survive. The danger is hidden behind the softness of the material. That is why water hits like concrete is such a powerful phrase, but it is also misleading. Concrete is hard because its structure does not flow away. Water is dangerous here because it flows too slowly relative to the speed of impact. The cause is different. The result can still be catastrophic. The camera moves underwater, the dummy enters from above, and a white bubble cloud follows. The impact does not end at the surface. Water is shoved downward in a turbulent plume. Bubbles collapse and expand. Shock waves travel outward. The path behind the dummy fills with froth. That bubble column is a map of energy. Some of the falling energy has gone into tearing air into the water. Some has gone into pushing water downward. Some has gone into surface waves. Some has gone into the dummy's sudden deceleration. The more violent the bubble column, the more energy the water has been forced to absorb. But the water is not the only thing absorbing energy. The body absorbs part of it too. A falling object does not simply hit water. It collides with a fluid that has mass, density, and resistance to rapid displacement. Density matters because water is much denser than air. Moving through air at speed feels like resistance. But air is comparatively easy to push aside. Water contains far more mass in the same volume. When a body enters water, it must accelerate that water out of its path. At high speed, the amount of water that must be displaced in a fraction of a second becomes a major barrier. The surface is only the beginning. The deeper the object pushes, the more water must be moved. But the first contact is especially brutal because the body still has nearly all of its speed. Before the path opens, the water is still in the way. A steel ball drops into water. At low height, it splashes and sinks. At a much higher speed, the splash becomes explosive. A sharp crown forms. A deep cavity opens. The ball transfers energy so quickly that the water cannot simply flow smoothly around it. It is slammed outward and downward. The same material behaves differently because the speed changed. Not because water changed identity. Speed changes the violence of the interaction. A hand pressed slowly into water feels almost gentle. The same hand slapped hard against water can sting. That everyday experience contains the whole principle. At one speed, the fluid yields. At another speed, it pushes back hard enough to hurt. A fall from a great height is that slap scaled into a full-body collision. The common misconception is surface tension. Surface tension exists. It allows small droplets to bead. It allows certain tiny organisms to stand on water. It helps shape the first skin-like behavior at the surface. But for a large, fast-moving body, surface tension is not the main reason the impact is deadly. The main reason is inertia and deceleration. Water has mass. Mass resists sudden acceleration. The body arrives fast. The water must be forced aside. The body stops quickly. Force rises. The surface tension myth makes the danger sound like a thin, invisible film. The real danger is much larger and more brutal. The entire mass of water in the impact path has to be moved, and the body has to lose its speed while doing it. A pane of slow motion water fills the frame. A flat plate strikes it from above. The water does not part instantly. It caves, brightens with reflected light, and then erupts. A shock ring forms around the impact point. The plate's broad face traps a moment of high pressure beneath it. The shape of the object matters. A narrow object can open a smaller path through the water. A wide object has to move more water immediately. A flat impact forces a broad area to stop at once. That can make the first deceleration far more violent. But shape is not a survival recipe. It is a physics variable. Professional divers, rescue specialists, stunt teams, and trained water entry experts manage body alignment under controlled conditions because they understand that entry shape affects force distribution. That knowledge belongs inside training, equipment, supervision, and strict safety systems. Outside that world, high-speed water impact remains extremely dangerous. The science can be explained without turning it into instructions. The camera cuts to two dummy tests. Zone dummy enters through a smaller leading shape. Another strikes broadside. The first creates a narrower splash column. The second creates a wide explosion of water. Both impacts are serious. But they show how the area of first contact changes how the water is pushed aside and how force spreads. The danger does not vanish because the body is vertical. The danger changes form. A narrow entry may reduce the first contact area, but the speed still has to be lost. The water still resists. The body still decelerates. If the speed is high enough, even a clean-looking entry can be dangerous, because the forces inside the body can still be extreme. 8 dangerous speeds. Water is not a cushion. It is a medium that must be violently displaced. The next scene shows a falling dummy beside a simple force visualization. No numbers are needed to understand the idea. The dummy gains speed as it falls. When it meets water, that speed has to go somewhere. If the stop happens over a long distance, the average force is lower. If the stop happens over a short distance, the force is higher. If the stop happens over a fraction of a second, the body may experience a brutal deceleration. A fall is not dangerous only because of height. It is dangerous because height becomes speed, and speed becomes energy, and energy must be transferred during impact. Gravity adds speed during the fall. The water removes speed during the collision. The body is trapped between those two facts. The surface appears, again, calm and mirror. Like that calmness is deceptive. Water does not look dangerous before impact because the danger is not stored in the water alone. It is created by the relationship between the moving body and the water's resistance. A quiet surface can become violent in an instant because the falling object brings the energy with it. The water does not attack. It refuses to get out of the way fast enough. A test dummy hits at an angle. The first contact happens along one side. The surface grabs that side first. Twisting the body, the splash spreads unevenly. The underwater bubble trail bends. A rotation begins. This is another hidden danger. If one part of the body stops before another, the body can rotate, bend, or fold under force. Water impact is not only a straight vertical stop, it can introduce torque. It can twist the spine, pull joints, force the head and torso in different directions, or concentrate loads in unexpected places. A body is not a rigid block. Different parts move differently. During impact, the water may slow the first contact area before the rest of the body has caught up. That delay can bend the body under its own momentum. Even without a sharp object, the internal stress can be severe. The camera cuts from the surface to the dummy's internal motion shown as a neutral, non-medical visualization. Outer shell stopping, inner masses continuing forward, then compressing. The point is simple. Stopping the outside is not the same as stopping the inside. When the surface of the body decelerates quickly, internal structures may continue moving for a fraction of a second. That is why blunt impacts can injure organs, blood vessels, and bones without cutting the skin. It is why a smooth surface can still be deadly. The body is made of materials with different densities, attachments, and tolerances. Water can hit everywhere at once. The body has to survive that sudden transfer. Another shot shows a large flat object striking water. The spray ring explodes outward. The object slows dramatically. The water beneath it turns white with bubbles. The broad contact pushes a huge volume of water down and out. The impact looks less like sinking and more like a collision with a moving wall. The wall is not solid. It is made of water inertia. A fast object must carve a hole into a fluid that does not want to accelerate instantly. For the first instant, the water behaves as a heavy resistant mass. Then it moves, breaks, sprays, and flows. By the time it has yielded, the impact force has already been delivered. That is why timing matters so much. The difference between a gentle splash and a destructive impact may be fractions of a second. The water eventually moves. The question is whether it moves soon enough. A bridge fall, a cliff fall, a failed stunt, or a high-speed water crash all share the same underlying physics. The scale changes. The object changes. The body position changes. But the central problem remains. A moving mass meets a dense fluid, and the speed must be reduced. At very high speed, the water surface becomes the beginning of a crash. The scene shifts to an aircraft touching water. The shot is not about instructions or survival technique. It is about scale. A plane meeting water at speed does not simply land on a soft surface. The water pushes upward violently. The fuselage must displace a huge mass of fluid. If one part digs in, the forces can tear structures apart. If a wing or engine catches, rotation can become destructive. Water is not runway. Water is a moving, deformable, heavy medium. It can support. It can flow. It can also punish speed. A small-scale model slides into water. The nose touches first, and the water climbs up around it. A wave rises. The model pitches, spray blinds the frame. The motion looks slow, but the forces are concentrated. The water does not cut like metal. It loads the structure through pressure. That pressure comes from forcing water to change motion. Fluids can transmit pressure in all directions. During impact, pressure builds at the contact area and spreads through the water and through the object. The faster the impact, the steeper that pressure rise can become. It is not just the visible splash that matters. Under the surface, Pressure waves move through the fluid. The camera returns to the dummy. A side sequence shows low-speed entry and high-speed impact. At low speed, the water opens around the dummy with a soft splash. The body sinks. Bubbles rise. The ripples spread gently. At high speed, the surface erupts. The dummy decelerates abruptly. The bubble column drives downward. The spray reaches high above the surface. The shock ring runs across the water, like a white crack, same water. Different speed, different outcome. The science is unforgiving because kinetic energy increases rapidly with speed. A modest increase in speed can mean a much larger increase in energy that must be managed at impact. The body does not experience height directly. It experiences the speed created by falling and the deceleration created by stopping. That is why the phrase "from high enough" matters. The higher the fall, the greater the speed before impact. Ignoring air resistance and other real-world factors, the greater the speed, the more energy enters the collision. The more energy, the more violent the displacement and deceleration. Air resistance may slow some objects depending on shape and position, but it does not make high falls safe. Tumbling, rotation, uncontrolled body position, and changing orientation can make the impact even more unpredictable. A dummy tumbles in air. Its shape changes before impact. Known shoulder hits first, the water catches it. The rest of the body rotates over the first contact point. The splash becomes crooked. The bubble trail twists. The deceleration is no longer evenly distributed. An uncontrolled fall is not a clean laboratory entry. It is chaotic. The body may be rotating, the limbs may be spread, the torso may hit at an angle, the head may move differently from the chest, the water may be disturbed by wind or waves. Each change affects how the impact force spreads. No simple phrase can turn that into safety. The only safe message is to avoid dangerous falls into water. The camera moves into a slow-motion droplet field. A wall of spray freezes in the light. Behind it, the dummy has already vanished below the surface. The viewer sees beauty. Then the bubble column below reveals violence. Water can make impact look cinematic, but the physics underneath is severe. A splash is energy made visible. Spray is water accelerated upward and outward. A bubble column is air dragged downward. A shock ring is disturbance racing across the surface. Foam is turbulence after the collision. Every visible detail is a trace of force. The narration follows the white ring outward. The ring moves across calm blue water, widening and fading. At the edge, the water still looks peaceful. At the center, the surface is chaos. That contrast is why the misconception survives. Before impact, water looks soft. After impact, water returns to looking soft. The violence exists in the moment between. AS surface can seem harmless because it has no memory. The dummy test repeats with a smaller object. A dense metal cylinder drops. It punches through the surface and creates a narrow cavity. A flat disc drops next. It strikes harder, splashes wider, and slows abruptly. The disc must push more water aside at the first instant. The cylinder opens a narrower path again. This is not a guide. It is a demonstration of contact area. The shape of the first contact changes the pressure distribution. A broad first contact increases the amount of water that must be moved at once. A narrow first contact reduces the initial area but can concentrate force along a smaller path. Different shapes create different risks. At high speed, none of them make water safe. The surface tension myth returns in one final visual. A needle rests on water because surface tension supports it. Then a heavy dummy falls nearby. The impact blasts the surface apart so violently that the delicate surface effect becomes irrelevant. The scale of the collision overwhelms the scale of surface tension. Surface tension can shape droplets. It does not explain the destructive force of a large body hitting water at high speed. The main actor is inertia. Water has mass. The falling body has energy. The stop is too short. The camera shifts to a simple animation, like physical model without turning into a cartoon. Object, water, arrows, compression zone. The arrows are not decoration. They represent momentum transfer. The falling body pushes down, water pushes back, water rushes outward. Pressure builds where the two meet. The body decelerates. If the body cannot tolerate the deceleration and pressure distribution, injury occurs. The formula can be simple. Force depends on how quickly momentum changes. Energy must be dissipated somehow. Stopping distance matters. Stopping time matters. The shorter they are, the more violent the event. The viewer does not need exact numbers to understand the danger. The slow motion footage already shows the equation. A calm surface becomes a burst of spray. A falling body becomes a stopped body. The missing time between them is where the force lives. Another comparison appears: stepping into a pool, jumping from a low-controlled height into supervised recreational water, and high-speed impact. The first is gentle because the speed is low. The second may create a splash but still involves far less energy than a dangerous fall. The third is a crash. The distinction is not water versus land. The distinction is speed and stopping. Land is dangerous because it does not flow. Water can be dangerous because it flows too late. A pool can feel soft to a hand and deadly to a fast-moving body because the body arrives with too much energy and too little time. The camera moves under the water again. Bubble cavity collapses behind the dummy. The collapse creates turbulence that churns long after the first impact. The surface above has already begun to calm, but below, the water still records the violence. This delay matters. The first hit is not the whole event. After entry, turbulence, rotation, disorientation, and secondary forces may continue, but the most decisive damage can occur at the surface, when speed is highest and the water first resists displacement. The beginning of the collision is often the harshest. The dummy is recovered in the controlled test environment. The shot avoids spectacle and returns to the physics. A smooth surface can still create a blunt impact. A liquid can still transmit violent force. A soft material can become deadly when speed removes the time needed for it to yield. The next scene uses a row of water tanks. Objects enter at different speeds. At low speed, clean ripples. Medium speed, tall splash. At high speed, explosion. Shock ring, deep cavity, bubble column. The pattern is unmistakable. Speed changes everything. Not because water stops being liquid, because liquid still has mass. A person watching from above may focus on the surface. A physicist watches the deceleration. A rescue professional watches the energy. A safety engineer watches the stopping distance. A doctor watches the internal load. They are all looking at the same moment from different angles. The falling body brings energy. The water resists motion. The body decelerates. The outcome depends on how violently those facts meet. Video returns to the opening image. The dummy falls again. This time, the viewer knows what is coming. The surface is not a cushion waiting below. It is a dense moving material that must be forced open. The dummy hits, the ring erupts, the bubbles drive downward, the spray climbs, the body stops. The water did not become concrete. The water remained water, but the body arrived with too much speed, and the stop happened too quickly. That is enough. The final image holds on the surface after the impact. The splash fades, the ring spreads outward. The water becomes calm again, almost innocent. Only a fading column of bubbles below the surface shows what happened. That is the danger of water at high speed. It can look soft before the collision. It can look soft after the collision, but in the instant of impact, it can hit harder than the body can survive.